Alright, we're going to be looking at a weak base and strong acid titration. So first we want to find the pH before we add any HCl. So we know that we have 100 milliliters of a 0.05 molarity NH3 solution. And our Kb is 1.8 times 10 to the negative fifth. Since it's a weak base, we're going to have to react it with water to figure out how much of it's going to break apart into NH4 and OH ions. Can ignore water. We only have our weak base. Now we need to set up our equilibrium expression and solve for X. So X is our OH concentration, and that's 9.49 times 10 to the negative fourth molarity. So POH is 3.02, pH is 10.98. Makes sense since it's a weak base, it should be above 7. Okay, going to try this next one on your own, thinking back to our weak acid ones. Alright, we have our 100 milliliters of 0.05 molarity, and we're adding HCl to that. So first we need to write our equation. They're going to react to produce ammonium chloride. We had 10 milliliters times 0.1 gives us 1 millimole, and 100 times 0.05 gives us 5 millimoles. React it and then divide by total volume, which was 100 plus 10, or 110 milliliters. So we get our molarities 0.0364 and 0.009. And we're left with a buffer. So our pH is equal to pKa plus log of base over acid. Okay, again you need pKa, so we need the Ka. And then take the negative log of it, so we get 9.25 plus log of our base concentration over our acid. pH then is 9.86. Alright, let's look at this one. We have our HCl reacting with NH3 again. We have 25 milliliters of a 0.1, so that's 2.5 moles, or millimoles of HCl. And our 5 millimoles of ammonia. What do you notice? We're halfway to equivalence. Again, if you didn't notice this, you could still solve it out. You'll get the same answer, you just do more work. If you're halfway to equivalence, pH has to equal pKa. We calculate our pKa in the last problem, which was 9.25. So try this one, restart when you think you have it. Same equation that we've been using. This time though, we have 5 millimoles of ammonia and 5 millimoles of HCl. Make sure you know that this is the equivalence point. So at the equivalence point, we're only left with our weak acid. Some of that weak acid is going to break up, but we don't know how much, so we're going to have to do an ice table, which means we need the molarity of our weak acid. Okay, and our equation is basically the opposite of what we had up there. Or you could just do the net ionic and write ammonia ion reacts with or decomposes into ammonia and hydrogen. Either one will work. So setting up ice table, because it's no longer reacting, it's just breaking apart or dissociating. We have an acid, so we need a Ka. So you have to solve for the Ka, which gives you 5.56 times 10 to the negative 10th. So X this time is our H concentration, and that's equal to 4.28 times 10 to the negative 6th. So pH is 5.37 then. Notice the equivalence point of a weak acid, a weak base strong acid is always less than 7 because you're left with only the weak acid. I'm going to try this one on your own and then restart. So write your equation. We have 6 millimoles, 5 millimoles, and 0. React it to completion. And assess the situation. We're going to need molarity. And we have HCl, which is a strong acid, and ammonium chloride, which is a weak acid. So if we have two acids, they're not going to react. Only the stronger is going to matter. So we can ignore the ammonium chloride. So pH must be equal to the negative log of our hydrogen concentration, which is also our HCl concentration. So pH is equal to 2.2. Okay, looking at this graph, we have a pH starting above 7. So we're starting with a base of some sort. Our equivalence point is less than 7, which means this must be a weak base. Because if it was a strong base, it would have been at 7, the equivalence point. And it's always titrated by the opposite. So if we start with a base, then it's titrated with an acid, and it's always strong. Other points, make sure you know max buffering is where it's rather straight. If our equivalence point is at 50 milliliters, then halfway to equivalence is 25. So this is where pH equals pKa. At the very beginning, you only have the weak base contributing to the pH. And any point after the equivalence, you only have the strong acid because you'd have a weak and strong acid, such as in the last example problem. So solve this one and then restart when you think you have it. So you have 1.024 grams of an acid, and we dissolve it in 70 milliliters. Your answer should be 64. Alright, so we titrate it to the equivalence point with KOH, and they want to know the molar mass of that acid. Okay, key there is the equivalence point. So the moles of acid have to equal the moles of base, because that's the definition of equivalence point. We know that it took 80 milliliters of a 0.2 molarity solution to reach that equivalence point. So we can figure out how many moles it took to get to the equivalence point. So it took 16 millimoles or 0.06 moles of KOH. So that means we must have 0.016 moles of acid. Plugging that into my mole equation, they gave me the grams was 1.024. So I can figure out my molar mass. So make sure you read carefully, because that key equivalence point, if you hadn't read that, it may look like you don't have enough information. Important things to note: the equivalence points of strong acid, strong base titration is 7, because you only have a neutral salt remaining and water. When you have a weak acid and you're titrating it with a strong base, then the pH is always greater than 7, because you're left with the conjugate of a weak acid, which is a weak base. And a weak base titrated with a strong acid's pH is always less than 7, because we're left with the conjugate of a weak base, which is a weak acid. Indicators mark the end point of a titration by changing color. Indicators are weak acids that are represented by HIN. H because they're an acid, and IN for indicator. So you want the color change or the end point to be as close to the equivalence point as possible. So you need to know that when the color change will occur. When it is a base concentration of 1, acid concentration of 10, or you're in an acidic solution, pH is equal to pKa minus 1. So if you're starting with an acidic solution, the color change occurs at pH equals pKa minus 1. If it's a basic solution, then pH equals pKa plus 1. And that's because the log of 10 over 1 is 1, or 1 over 10 is negative 1. So here's an example of that. We have bromoethyl blue. They gave us its Ka value. It's yellow and it's blue. And it's in an acidic solution. So since it's acidic, we're going to use pH equals pKa minus 1, because we have more acid than base. Our pKa is negative log of 1 times 10 to the negative 7, or 7. So 7 minus 1 gives us 6. If we were titrating a strong basic solution, so if we had put this in a strong basic solution, then we would have used the opposite equation, pH equals pKa plus 1. So pH would have equaled 8. And also that you should know that since this indicator is yellow in its acidic form and blue in its basic form, it would start off yellow and turn blue at a pH of 6. So again, you want the endpoint and the equivalence point to be as close as possible. Alright, in this problem you have 3 Kas of indicators. We want the titration with the equivalence point greatest to 3.5. So you figure out your pKa, and your range is plus or minus 1, that number. So because we want an equivalence point of 3.5, the second one would be our best option.